Hey everyone. You ever hear about a discovery that just makes you question everything you thought you knew?
Oh, yeah. Definitely happens all the time in science.
I mean, that's kind of how I felt reading this UCLA article
Uh-huh.
about these chemists who basically might be rewriting textbooks.
Yeah, this is a pretty big deal. It has to do with this fundamental rule in organic chemistry called Bredt rule. Been around for over 100 years.
Okay, so just to make sure we're all on the same page.
Right.
Organic chemistry, we're talking about carbon-based molecules.
Exactly. Yeah, like the stuff that makes up, well, everything. Us, materials we use, you name it.
And one of the really important things in organic chemistry is the carbon double bond.
For sure. It's this special bond that gives molecules all these unique properties and makes them super useful for building complex structures.
Okay, so then Bredt rule, it basically said you couldn't have this double bond in certain spots, like in a molecule.
Right. It's kind of like, I don't know, trying to jam a square peg in a round hole. It just wouldn't work.
Yeah, okay, I get that.
So Bredt's rule, it really focused on these things called bridgehead carbons. Just picture them as the keystone in an archway, right? Holding the whole thing together.
Okay, I'm picturing it.
Now, try to imagine adding a double bond there, like bending that keystone. It just shouldn't work.
Okay, that makes sense.
But the thing is, for a whole century, chemists just accepted this as, the truth.
Until now.
Well, yeah. So you have this UCLA team led by Professor Neil Garg, and they're like, what if we challenge this? And they went and actually created these molecules that were thought to be impossible. They call them anti-Bredt olefins.
Hold on, they broke a rule of chemistry. That's crazy.
Yeah, pretty amazing. They used this specific type of molecule, sort of think of it like a special ingredient that let them force a double bond where it's not supposed to be.
So, they found a way to bend that keystone without the whole arch falling apart.
You got it.
That's wild. But I'm guessing it wasn't simple, right?
Yeah. No, not at all. The biggest problem, these anti-Bredt olefins, they are super unstable. They just don't want to exist. They fall apart super fast.
Okay, then how do you even know you made them if they're gone so quick?
Well, that's where it gets really clever. They set up this sort of molecular trap. It's like if you were trying to catch a rare butterfly, you'd need a special net. Right.
Yeah, okay, that makes sense. But why go through all this trouble? What's so special about these things anyway?
Well, Professor Gerg says it pretty well in the article. There's a big push in the pharmaceutical industry to develop chemical reactions that give three-dimensional structures because they can be used to discover new medicines.
Wait, so this could mean new drugs, new therapies.
Exactly.
Okay, so this is where it gets really interesting.
Yeah. So you see, the shape of a molecule is super important when you're developing drugs. Imagine
Yeah.
Okay, so a lot of diseases are caused by specific molecules in your body that are kind of going haywire, like a tiny machine with a broken part.
Okay, I can see that.
And drugs, they work by targeting those broken parts, fixing them or stopping them from doing more damage.
Right.
But to work, the drug has got to be just the right shape to fit onto that target.
Like a key fitting into a lock, right?
Exactly. Now imagine you're designing a key for a really complex lock. Tons of twists and turns. You'd need all sorts of tools to make that key fit perfectly.
Okay, that makes sense.
So these anti-Bredt olefins, they're like new tools in the toolbox. They let chemists build drug molecules with even more complex shapes, more features, like adding extra grooves and notches to that key.
So you can fine-tune it even better.
Precisely. And that means potentially better drugs that are more effective, fewer side effects, maybe even drugs for diseases we couldn't treat before.
That's amazing. But I'm sure not everyone was immediately convinced by this, right? To go against a rule that old.
Oh yeah, there's always going to be some pushback when you challenge something that's been around for so long.
There's this comment on the article from someone named Calvin, and he's like, wait, are you sure these things even exist? He thinks maybe they misinterpreted their data.
Right, and that's actually a good thing. It's healthy to have that skepticism. It forces scientists to really defend their work and make sure their discoveries are rock solid.
So it's not just one team says something and everyone's like, okay, cool, we believe you.
No, not at all. Big discoveries, especially ones that challenge the norm, they go through this intense scrutiny from the whole scientific community. It's called peer review.
Okay, what's that?
Basically, before a study can get published, it has to be reviewed by other experts. They examine the methods, the data, everything to make sure it's legit.
So it's like a quality check.
Exactly. And in this case, the fact that the UCLA team's research passed peer review and got published in a big journal like Science, that tells you something.
So even though Calvin has his doubts, other scientists have looked at this and they're like, yeah, this seems solid.
Right. Which doesn't mean the debate is over, but it does mean the evidence is pretty strong. And, this is just the beginning.
There's more.
Oh, yeah, lots more. This discovery has opened up a whole new world in chemistry, and we're just starting to explore it. That's what we'll be getting into in the next part of our deep dive.
Okay, I can't wait. This is shaping up to be one of our best deep dives yet.
I think so, too. Lots more to unpack here.
Welcome back, everyone. So before the break, we were talking about how this discovery could totally change how we make new medicines. It's hard to imagine something thought impossible could lead to so many new possibilities.
It really shows how science is always moving forward, right? What's impossible today could be reality tomorrow.
Okay, so can you remind me why this is so important for making new drugs?
Sure. So remember how a lot of diseases are caused by specific molecules in your body going wrong? It's like imagine a tiny machine where one part is broken.
Okay, yeah, got it.
And drugs work by targeting that broken part, right? Either fixing it or stopping it from causing more damage. But for that to happen, the drug molecule has to be shaped just right to interact with that target.
Like a key fitting into a lock. We were talking about that.
Exactly.
Yeah.
Now imagine you're trying to design a key for a really complicated lock, like one with tons of twists and turns. You'd need a lot of tools to make a key that fits perfectly.
Makes sense. So how do these anti-Bredt olefins help with that?
They give us more tools. By putting double bonds where they weren't supposed to be, chemists can create drug molecules with way more complex shapes, more detail. It's like adding grooves and notches to that key so it fits even better.
So it's like they unlocked a whole new level of customization for designing drugs.
Yeah, exactly. And that could be a game changer for treating diseases that have been really tough to treat before. Think about it. Drugs that work better, have fewer side effects, maybe even cures for diseases we couldn't treat at all before.
That would be incredible. It's like having all these new weapons to fight diseases. But it's not just about new drugs, right? I read that this could also help us improve existing medicines. How's that work?
You're right. A lot of the drugs we use today come from natural sources like plants or fungi. These naturally occurring molecules are often super complex, and it can be really hard and expensive to recreate them in the lab.
So it's like trying to, recreate a famous painting, but with molecules.
Perfect analogy. But with the ability to create these anti-Bredt olefins, chemists might have found a way to simplify that process.
So we could make life-saving drugs cheaper and easier for everyone to get.
That's the hope, anyway. It's early days, but the potential is huge. This could totally change how we develop drugs and make people's lives better.
This is seriously mind-blowing. Who would have thought that a basic rule in organic chemistry could have such a big impact? It shows you how connected everything in science is. Even small discoveries can lead to huge breakthroughs.
Definitely. And it's a good reminder that in science, you always have to push the boundaries and question what you think you know. Sometimes the most amazing discoveries come from challenging the things we thought were set in stone.
So what's next for scientists exploring this new area?
Well, one of the big challenges is figuring out how to better control and stabilize these anti-Bredt olefins. Remember, they're still really unstable and break down easily.
Right, they're like those little rebels. So they need to figure out how to, tame them or something.
Exactly. They're working on new techniques and strategies to create them in a more controlled way and keep them from breaking down.
Sounds tough. So once they figure that out, what other areas will they be looking at?
Well, besides their use in medicine, these anti-Bredt olefins could be useful in all sorts of other fields, things like materials, science, energy storage, even agriculture.
Wow. So we might be seeing these molecules popping up everywhere. It's like a whole new world of possibilities just opened up.
It's a really exciting time to be in chemistry. Who knows what other unbreakable rules we might challenge next?
This has been amazing. We've learned so much. But I know there's still more to cover, right? What else is there to discover about these anti-Bredt olefins and how they might change the world?
Well, there are some important things to consider, like the risks and challenges that come with this discovery. We also need to think about the ethics of creating and using these molecules.
That's a great point. Progress always needs to be balanced with responsibility. So let's dive into those aspects in the final part of our deep dive. So we've talked about all the amazing things these anti-Bredt olefins could do, but you also mentioned some potential risks and challenges. What are scientists thinking about as they keep working on this?
Well, the big one that comes to mind right away is safety, These molecules, they're really reactive. That's what makes them so interesting. But it could also make them kind of dangerous. Scientists have got to be super careful when they're working with them, especially since we're still figuring out how they behave.
Yeah, it's like exploring a new, uncharted territory. Got to be careful and ready for anything. What are some other challenges?
Figuring out how to actually make these molecules in larger amounts is a big one. The ways we create them right now are very specific and kind of expensive.
Yeah.
If we want to use these in like real-world applications, medicines, or new materials, we need to find ways to produce them more efficiently and for less money.
It's like you've got this recipe for an amazing dish, but it's super complicated. To share it with everyone, you got to simplify it. You also mentioned ethical concerns. What are some of those?
Oh, yeah, that's super important. With any new powerful technology, there's always that chance it could be misused, right? So we have to think carefully about how these molecules could be used, who has access to them, what safeguards need to be put in place so they aren't used for, bad stuff.
It's a good reminder that science can't just move forward without thinking about the consequences.
Yep.
We need to have those tough conversations and make sure these discoveries are used for good.
Totally agree. And those conversations need to happen early on, not just with scientists, but with ethicists, policymakers, the public, everyone.
Wow. This has been such a fascinating deep dive. We've learned so much. From like basic organic chemistry to these anti-Bredt olefins that could change everything. What's the one thing you really want listeners to take away from all this?
I think the big takeaway is that science is always pushing the limits, challenging what we think we know. This discovery is like the perfect example. Who would have thought a rule that lasted over 100 years in organic chemistry could be broken? It just goes to show how important curiosity, creativity, and that drive to learn are.
And it reminds us that there's always more to discover, even in areas where we thought we had everything figured out. Maybe someone listening right now will be the one to make the next big breakthrough.
That's the beauty of science. It's an adventure, always something new around the corner.
This has definitely made me think, and I hope it's done the same for you. If you're interested in learning more, you can find a link to that UCLA article in the show notes. Keep exploring, keep asking questions, and never stop learning.